more than half of you. All right, so this is our last. Actually, I'm going to leave this visible for a second. We've got a couple of remoties. I'm going to cover this up so you don't have to talk into the projector. And when it's these guys' turn, we'll unmute them. We'll unmute the projector. So this is a culmination of the term. And the basic idea is, some of you have done some kind of lightning talk before. It's just 2 minutes about basically whatever you want to talk about. But usually people talk about the research, and we try to hold it to 2 minutes as much as possible. Usually people are very good about that. Actually, most of you in the first, which is excellent. But this is the order that you registered in. As I said, we've got some remoties. This is Nidhi Rastogi. This is Tim Lebo, Tim RDF, the creator of the converter. There are a couple people who are on the list, but I don't see here. I don't know what the deal is, but they, in the case of Eric Ameras, he's not a frequent TWedder, so you might think it's at 7. So we'll see. But without further ado, let's get started. I'll take it away. And I don't know if somebody could help me keep track of time. That would be really awesome. Keep track of the run length, because I tend to have to juggle things. So just come on. And no notes. Remember, the rules are no notes, no props. Don't worry about what's behind you. Don't worry about what's behind you. Just
hello, everybody. My name is Hao John. I'm second-year graduate student under Professor Fox, and one of the biggest achievements of this semester is to attend the lightning talk today and give you guys a little talk. Yeah, so in the domain of material science, there's a project called NanoMine, which aims to develop a living open source data platform for collecting and presenting data in nano composites, like nanomaterials. And in this project, the existing literature data on nanocomposites are being curated and formatted and stored in a developed system and for people for further use of the data. And in this process, a person in computer science is needed, which is me, for this summer to help them to develop an ontology on these nanomaterials and build a front end that enables searching, summarizing, and also sort of features. And that's the internship I'm going to do this summer. Thank you.
All right. And another rule is you crush.
Yes, let me talk.
Yeah. Thank you. You didn't. So I'm serious about no notes. All right. Master. Snapple, right?
Snapple. The best stuff on it. Hello, everybody. So in the past several years, IBM has been developing a new type of computer chip called the IBM True North chip. This is a non-von Neumann computer chip that boasts very high power efficiency when compared to traditional CPUs or GPUs. And so one of the things that IBM wants to do, obviously, is get people to develop applications for this chip. The chip is, quote-unquote, inspired by the human brain, and it lends itself very well to deep neural network applications. But some of the challenges associated with the chip are constraints that are imposed by the hardware of the chip. So for example, if you're creating a neural network model that you want to run on the True North chip, you cannot have any one neuron connected to more than 256 other neurons. All the weights between layers in a neural network must have discretized integer values. And it is a spiking model, meaning that rather than continuously generating output, the neurons will accumulate voltage to a certain level and then fire once they reach a voltage level above a threshold. So in order to convert between some well-known continuous neural network model to a model that will run on the True North chip, you need an intermediary step. IBM has a program which does this called T, but it does it only for the IBM architecture. So what we would like to do is create a program that converts between any feed-forward neural network to any spiking neural network model with some hardware constraints imposed upon it. And we're calling that application Snapple, which is similar to, inspired by the name of T that IBM came up with. Currently, we have achieved the ability to unroll recurrent neural networks and convert them into feed-forward, which is an important first step when you want to convert between some generic neural network model and the type that respects the hardware constraints. And in the future, we plan to implement the ability to convert between continuous to discrete weights and non-spiking to spiking networks. Thanks.
Very cool.
I almost screwed up.
Have you seen the talk by the guy who implemented the convolutional neural network on just analytical engine?
No.
This is a very cool talk. I'll find it for you. Does anybody listen to that? It's awesome. Some British grad student. Yeah.
So, however, instead of my own research, I will talk about the one data science competition I was in April. So actually, Anirudh was also in the same team with me. So the background is about the city bike rental program in New York City, and all the historical usage data was given. So for each station, and the target is to see whether where a new bike rack is needed for a new location. I think we first of all we define our own target as the frequency of use time times the unavailability of bikes for each station, and and then we scale the target and the dependent variable as a number from 0 to 1, and then based on our own observation we choose the threshold 1 to 5. If it's less than that, it's a 0, and if it's more than that, it's a 1. So eventually we turn this problem into a binary classification problem, and then we use all kinds of available like open source data online and APIs to get our independent variables, the features. So for example, we use the because for each station the longitude and latitude were given. So for example, we use the Google Elevation API to get the elevation for each station, and also the Foursquare venues API to get the for example the number of venues for each station within 100 meters. So eventually we get around 10 features. These are all location based. So for example, the distance to the closest subway station and the number of landmarks within 1 kilometer, something like that. And then we run 5 to 6 kinds of different kinds of supervised learning classification models, and based on the RC chart and the confusion matrix. So we choose the model with the best result, and then later on we can use the model to predict. So for a new location, if the longitude and latitude is given, whether the probability of a new bike rack is needed is whether the probability is high or low. So.
Thank you. How long is that?
220.
If they go too long.
I'll give you the signal if it gets broken.
I've been thinking of putting it up on there. Go ahead.
Hello, everybody. I'm Kara Reedy. I'm a first-year student working with Jim Hendler. My main project this year has been working on an artificial life simulation, meaning that I have the simulated environment with a bunch of different objects in it and a bunch of creatures running around in that environment that can interact with these objects in different ways. They all have brains powered by neural networks, so the hope is that they'll be able to learn through their experiences and have happy and long lives, which is very often not actually the case for things. Usually they end up starving to death. But well, one of the aims of this project is to eventually see if we can get it implemented and running on IBM's new neuromorphic computing hardware, like Matt was talking about. What I've been working on this semester has been on planning and designing a genetic system to bring in this new dimension. And the plan is for it to not only encode the weights of the neural networks, but also the structure, and for it to be a diplogenetic system, meaning that there are 2 copies of each gene rather than just one. This introduces a lot of interesting and new complications, but it also means that you can see interesting effects like dominant recessive traits, and it could also potentially lead to more stable fitness over time.
All right. So what's a happy life for one?
Running around playing with other creatures, not dying of starvation.
Because I think you could have a potential happy short life.
Certainly.
All right, so Nidhi is next. Hold on.
Yes.
All right, so Nidhi, you gotta go on video.
Yeah, I'm trying. I think I turned off some settings and it's just not turning on. I don't know why. But anyways, I'll still not waste my time and everybody else's. So I'll just go right ahead. So the topic for today's my lightning talk is using information centrality for anomaly detection. Centrality basically means identifying the most important node in a graph, and there are several algorithms which do that, like betweenness, closeness, degree, and there's another one called information centrality, and that's the one that I'm using for my research. So centrality, basically, the idea is to rank nodes in a graph in decreasing order of importance and then run an analysis on the top few. So with my research, we identify anomalous behavior using those top few central nodes, which is by comparing the baseline behavior of a network in a given time period and then check for any anomalies in comparison to the baseline behavior. So using existing standard information centrality algorithm, I ran this algorithm on an IBM provided data set last summer and tested for its working on static network data set, and found that it could be used for identifying some central nodes, but how the behavior was useful in identifying anomalies was yet to be seen. So because it was done on static data set, nodes data set of that network. So, but now what I'm doing is I'm running the same algorithm, the standard algorithm on freely available data set of the configure malware, which basically creates denial of service attack by pinging repeatedly on port 445. And what I'm doing is running this algorithm and seeing that if I'm able to find central nodes over a period of time, does it really help me identify this particular attack? So once I have interesting results, I'd love to share them. Thank you.
All right.
I saw that. Thank you.
All right. Andre.
Thanks, John. Hello, everyone. My name is Rayan. I'm a fifth-year PhD student here. So during the last year, I've been working on a new area called stream reasoning. So what it does is basically try to combine the power of semantic reasoning and stream processing. So basically doing the inference against the streaming data. So this is a fascinating area, and there's lots of work, and there's like a lot of areas to be unexplored. So I'm really excited to work in this area. So during last year, I've been working on a concept called semantic importance. So this concept has been proposed since this January, and so why I proposed this concept is because it is really important to consider which part of data to evict when you're presenting the streaming data, especially in a semantic way, because due to the boundlessness and the exploration kind of feature of the streaming data, and we usually use a limited space to process the data. And when you process the data, you want to get the most of the data for the query execution, right? So if the data exists earlier, and if that data is needed for the query, then you probably won't get the result. So you basically want to identify which part of data is important, that more important than other data, and then you manage to preserve them until the other component part comes into it and give you the query result before everything expired. So this is kind of the idea. And so that's why I developed this content, semantic importance, to describe the contribution and potential of the data that can contribute to the query result. So I basically developed like 5 subcategories, including timestamps, expression timestamps, generation timestamps, the arrival system timestamps, and also the query contribution, including reasoning participation frequency, recency, and query participation frequency and recency, and also the use case requirements. Because when you process the data and the query, everything is going to the use case. So that's kind of 3 main parts I'm exploring. So how much time do I have?
You're on that.
Yeah. So yes. So that basically. So we are working on a paper that processed the soccer data, streaming data that streams the players' position data, and then we are trying to use our technology to detect who commits after the offense, and we are submitting this paper to CIK. Thanks.
Hello everyone, my name is Ahmed Elaish and I'm a PhD student with Professor Fox, and last time I was here I talked about how we were trying to detect and classify fossilized protozoans in images of geological samples. Now, over the course of 2 projects, we were able to accomplish that to an extent. So it happens over 2 phases. The first would be the detection of the fossils. What we do is we use an approach of superpixel segmentation, and what that means is that we try to group pixels into groups of pixels called superpixels that are similar in intensity and close to each other. So first we apply a method called simple linear iterative clustering. That's a type of k-means clustering that tries to cluster the pixels, the smaller pixels, into groups that are similar to each other. Following that, we apply a method called normalized cuts, which looks at all the segments and their similarities and focuses on the objects and the edges within the image. So it really localizes the specific objects, fossils and otherwise other material that we might not be looking for. We then run these segmented images into a weak classifier, just using color histograms of known fossils so that we can separate images of background that we don't need. And out of this process, we get a few images from each sample that represent fossils or objects of interest that are very similar to fossils. We just train a few classifiers on, we tried a range of 9 different features, some based on texture, some based on the color and distribution of the color of the object, some based on the shape of the object. And we found a good combination of those features. We trained a few classifiers, and the best accuracy at the data set is relatively small. We have 106 positive and 106 negative samples, and the highest accuracy we got at classification was 80% using KNN. And I would say that is because even the fossils themselves, they have some differences. They're not all alike. Some, the same fossil might look different on either side. So they might be subdivided into 2 classes themselves. So KNN really captures the similarities in local neighborhoods rather than on a global scale. So we accomplished quite a bit and might be taking this forward. That's it. Thank you.
All right. Oh, she wasn't feeling well. Yeah. Oh well.
Hi everyone, I'm not Katie, you can see that. But, so my name is Anirudh Prabhu. I'm going to talk to you all about narratives and situation calculus. Before I get into that, 2 terms that you should probably know. One is situation calculus. It's a logic framework for representing and reasoning about dynamic domains. Second is probably what's a situation. So a situation is a snapshot of the world at any particular time t. So getting into narratives, one of the formalisms of situation calculus by John McCarthy deals with 3 major problems. One is narratives, 2 is planning, and the third one is predictions. So let me start with narratives. A narrative is a story, or it's basically a history of what happened until now. So what we want to do is use these narratives as a starting point to further apply reasoning. So how situation calculus works is you give the model information about a situation, and you give it general laws on the effects of actions, and you're able to infer information about future situations. So narratives are very useful in this aspect. And since you know that situation is a snapshot of the world at a particular time, at any point in time t, you have so many different narratives going on concurrently. So these narratives may be independent to each other, or they can be dependent to each other. In the case that they are dependent to each other, you need to combine them into one narrative and arrange them by their ordering in time. So there are formalisms for this, but all of this is sort of done manually. You look at a story, hear it, you do something, and then you write the narrative down and use the formalism to manually combine it. So this summer I want to basically work on a project, and this is probably an elevator pitch for it, that automates the whole process that I just mentioned. So you get data, text data, audio data, video data from a particular source. In this case, I have a source. Professor Fox is providing the data from a particular project, and we use this to generate a narrative in situation calculus, and then we combine the narratives. Okay, I'm almost done. We combine the narratives using some sort of automated tool, and then we can go on to the next steps, which are planning or prediction. That's pretty much all I have. Thank you.
All right, so let's see if we can somehow get Tim up and running here. Hold on, Tim. We see you, but we see you as muted, but I think we can unmute you. I don't think you're muted. Try talking, Tim. No. So let's try this. Hold on.
Hello.
There we go. We hear you.
Okay, I'm going to mute myself. Oh, it doesn't matter. Hello, my name is Tim Lebo, and I can hear myself really poorly.
I will mute that. Sorry about that, Tim.
Hello? I guess I can just talk through myself.
Just go. All right. Let's go to. We'll cover up.
Hello, my name is Tong Tao, and I'm working on multimedia information extraction. This matter, I'm mainly focused on a cross-media joint model. Before that, until last December, I was doing cross-media inference, which is to say, I read a news with video or with image. The news is about a very heavy event, but there might be some mistakes from the vision detection system. Say, okay, I saw an ambulance or firefighter in the image, so I want to use inference to cross out those bad results. But the problem is when I say inference, automatic inference, I have to set a point where which I have to trust. For example, I trust my automatic system on the news media, on the news document, I mean on the text side, or I set a point on the vision side. So to solve the problem, I just don't want to set like the trusting point. I just use a joint model. I will extract features from both text document feature and also from the video feature. I want to merge them and try to eliminate the bad results and try to enhance the good results. So that's how a cross media model works. Okay, thanks. Thank you very much.
Press off, Tim.
Hi, I'm Robin.
Hi, Robin.
This is my Chinese name. So this time I have actually, during the past whole year, I've been digging the JSON LD, which is called JSON linked data. It is a linked data format origin basically in JSON, but also provides the linked data feature. So we know nowadays we frequently or widely use a lot of web APIs or web applications to try to grab and capture data on the web and turn that into linked data. So the benefit of this is linked data will empower people to publish and use or even reuse data on the web. And actually it's a way to create a network of first standardized based and also machine readable data across the whole internet. So, but a problem of this, like significant issue of this is for most of the web applications, it's not RDF friendly because RDF basically does not support lists, which is like the most popular data structure used by people in all the majority programming languages. So by taking use of JSON LD, we can easily, for example, I write a neural network model, train it in, like even in JavaScript, and post it, deploy it on the web as a web application. And then I turn the output, easily convert it into RDF or RDF graph and store it in a triple store, which is like not easy to do in the past if we just dealing with RDF or triple store Sparkle itself. So I'm keeping working. I've been keep working on that. So it's probably turns out to my thesis topic in the future. Thanks.
All right. I'll crush it. To reinventing the list for your thesis.
Hello, everybody. My name is Bo Liang, and I'm a third-year PhD student from Professor G's group. And this semester, I am working on information extractions for low-resource languages. At the starting point, we decided to implement the name tagging system for the low resource language. So low resource language is kind of actually it doesn't mean a language that not many people speak it. It's just it's a language that not many people have been doing research on it. I mean, on the natural language processing side. So it doesn't have many resources and annotation data. And the name tagging. A name tagger is sort of like trying to tag the name, location, and organizations in news documents or tweets or some other journal. So the challenging part is we don't have much resources for the language. And also, actually, we have an evaluation on this August. And before the evaluation actually lasts for 1 month. And before the evaluation, we don't know what language we will get. So that's the most challenging part. And so what we are doing right now are trying to make it as general as possible. So all the resources we use, like a Facebook, which contains 200 or 300 languages, and the survival guide, use this, which also are in many languages. So use these resources as either annotated data or gazetteers or dictionary to do supervised training, semi-supervised training, and yeah, that's pretty much.
Is there a set of possibilities of the language, or you absolutely have no clue what it is?
No clue.
Wow. So it could be anything.
Yeah, yeah. It could be.
So he's not here. All right.
Hello. Hello everyone, my name is Zhicheng Liang and my English name is Jason, and I'm a first year PhD student working with Professor McGuinness, and for this semester I took part in the TWed projects in which we have some tags called semantic annotation. The semantic annotation we are doing is to annotate a bunch of data sets, which is originally is kind of something like spreadsheets. So in every column they have the description for the column. So we want to use some techniques to match those columns with our ontology. So in this process, we used some NLP techniques like universal dependency parsing and some synonym word replacement and some kind of techniques when we process the text. So the biggest challenge for the semantic annotation is that when people write the data column descriptions, they may be very casual, so it's hard to capture the subjects and objects in the sentence, so that we can know which entity they are talking about. So maybe in the future we should apply the more techniques. We are going to use some kind of topic modeling and some and the word2vec to the word2vec tool to capture those features that are related to the sentence. And another thing I'm doing is the cheer project. So we are integrate the header tag and a kind of links tool which is called a lab key to manage the metadata in our cheer projects. So this is what I have done in this semester. Thank you.
Good job, Jason. I about had a heart attack when you started talking about heart attack. Is that your first lightning talk?
Huh?
Was that your first lightning talk?
Yes.
All right. So we're supposed to have Eric Amaris on. Is he on? I don't see him on. Again. I was going to say something about Sideshow Bob. I don't know. What do you do? What do you do? All right, I'll be Bart to your Sideshow Bob. How's that? Where okay. Where are these guys? So the sun. Yeah, we'll cover you up. You're so shy, Tim.
Hello everyone, I'm Bassam Mahdi and I'm working on deep learning for semantic reasoning. So after a few years of wait, neural networks are coming back and trending again, and the main reason behind this comeback is the deep learning movement. What is special about deep learning is, unlike other machine learning techniques, it doesn't require a good choice of features, but it can learn the features by itself. So for example, if we apply a deep learning network on the MNIST database, which is the database of handwritten digits, you'll find that the first layers can learn the pen strokes, and the upper layers will detect which digits was it. So because of this nice feature, deep learning is successfully used through a wide range of applications, from image detections, image classification with convolutional nets, to machine learning for natural language processing with recurrent networks and speech recognitions, etc. So if we are dealing with the sequence of our input is a sequence, like in the case of natural language processing, we used recurrent networks. This is sequence learning. But if our input and our output is sequence as well, like in the case of machine translation, like we have sentence source and the sentence target, we use sequence to sequence learning. So what I've been doing in the few past months is to apply sequence to sequence for semantic reasoning. So for example, if the input is, if A is subclass of B and B is subclass of C, the output will be that A is subclass of C. So I've been having good results with RDFS rules and a good subset of our rules. So what's next in our applications, as Matt was mentioning, is human brain inspired shifts. So we are having paradigm shifts in the architecture. We are not using the volume architecture anymore, but we are using these human brain frameworks. So these frameworks, like the True North IBM, is projected to be applied in the self-driving cars, etc., in the near futures. So our ultimate goal is to apply what you call machine ethics. Okay, I'll not talk about machine ethics.